Hello, welcome to the fourth installment of this video series on fields. Today we're going to talk about field strength. In particular, we're going to look at the gravitational field strength, which is force per unit mass, and the electric or electrostatic field strength, which is a force per unit charge. Look at Arnie's guns there. Now let's compare these side by side, gravitational field strength and electrostatic field strength, similar to what we did last video. Now, the gravitational field strength is, as I said before, the force per unit mass. And the electrostatic field strength, or electric field strength we often say, is the force per unit charge. So another way of thinking about this is, what is the force on 1 kilo due to a field at any point in space, or at a point in space? So further out, the field will be weaker. Closer in, the force will be higher on 1 kilo, so it will be larger. So force on electrostatics will be now the force on 1 coulomb due to a field at any point in space. So what happens to that 1 coulomb as you go further or out in a field? Now the formula for it is going to be G, which is gravitational field strength, little g, is equal to force divided by that mass in that field. Electric field strength is going to be force per the little charge that is in that field. Okay, so we had previously the Newton's law of universal gravitation. We can then derive our formula of little g being equal to G big M on R squared. And for electrostatics, we can use Coulomb's law, and we can get the electric field strength to be kq on r squared. So it's actually independent of the little mass itself, or the little charge. This rule here, this final rule that we came up with, was due to a point mass field or due to a point charge field. Okay, as you can see in the diagram here. Looking at here, we can see you can use that rule, G equals Gm on r squared, and it'll tell you what the force will be on that 1 kilo mass at a particular distance from the big mass there. Or with the big cube, you can tell us what the field strength is on a 1 coulomb mass due to that charge there. Okay, let's do a fun fact. It's got to be Arnie, doesn't it? He can squat 245 kilos with his quads of gods. He can bench 225 kilos, those guns there, and he can deadlift 320 kilos, which is absolutely ridiculous. Alright, back to physics. Now let's look at point charge and the electric field strength with distance here. First of all, imagine we've got a big Q, or the central charge, as being 1 microcoulomb. And what's the field strength as we get further away from at 1, 2, 3, and so on, up to 10 meters? Okay, putting this in our formula here, we know K is 9 times 10 to the 9. The charge is 1 times 10 to the minus 6 coulombs, and divided by R squared. Now, we know R squared to start with is just 1 meter. So what's the force on a 1 coulomb charge at 1 meter? It's going to be 9,000 divided by 1 squared, solving all that set of equations there. So we'll put 9,000 newtons per coulomb. So it's going to have, for every coulomb that's in that position, it'll have 9,000 newtons on it. Okay, jumping across, we've done 2, which is 2,250, 3, which was 1,000 newtons per coulomb. We're going fairly quickly through here. 4 squared, we get 562.5 newtons per coulomb. And 5 squared, so at the distance 5 meters, it's 360 newtons per coulomb. At 6 meters, we're going to have 250 newtons for every coulomb that's there. At 7 meters, we're going to have 183.7 newtons for every coulomb at that position. And 8 meters, we're going to have 140 newtons per coulomb. And 9 meters, we're going to have 111.1 newtons per coulomb. And finally, at 10 meters, we're just going to have 90 newtons per coulomb there. Okay, so as you can see here, that's the 1 on r square relationship, and you can see that the electric field strength really drops off with radius there. Okay, now let's go to a gravitational example. Hopefully you watched the previous video and you would have worked out that we found the force at the surface of the Earth on a 1 kilo mass to be 9.81 newtons and 8.95 when you are 300 kilometers above the Earth's surface. This might ring a bell now, hey. So the force is gm little m on r squared. And little g is the force per little mass, or on a kilo of mass, per kilo of mass. So this is actually the same formula when m equals 1. Okay, so g is actually just equal to 9.81 newtons per kilo. And we should refer to this as the gravitational field strength is 9.81 newtons per kilo, and the acceleration due to gravity is 9.8 meters per second squared. Similarly, at 300 kilometers above, it's 8.95 newtons per kilo. This really ties in now to a bit of a digression, but general relativity and the idea that acceleration and also gravitational field strength are equivalent, and that we can't actually tell the difference between accelerating at 9.8 meters per second if we're in a rocket, or being in a gravitational field. Okay, now back to fields. Gravitational field strength, let's define this in summary, is the force per unit mass. It's dependent solely on the position and the field created, and not the mass in that field. Similarly, with electrostatic field strength, it's the force per unit charge, and it's dependent on the field itself and the position in the field, but not the charge in the field itself. Okay, so thanks for watching this particular video. I hope you now understand field strength. It's a little bit of a tricky concept, so feel free to go through this video again, and subscribing is sincerely appreciated. I hope you'll definitely watch the next video and leave some comments below. Thank you.